Hello, welcome back. So, we kind of started talking about a little bit about the energy equation, right? So, we kind of next headed to thermal boundary layers. So, typically when we talk about boundary layers, we are usually talking about how the velocity profile changes, across the boundary layer, and how do we define a boundary layer in terms of, how the velocity profile, right, looks like, is zero at the boundary, and then reaches free stream at some distance away from it. So, how do we sort of define that? So, those are things that we've been concerned about. So, those are things we've been sort of concerned about so far, right. So, there is something also called a thermal boundary layer, because we also need to take into account the fact that there will be a certain transfer of there will be a certain transfer of, say, temperature, or there will be a difference of temperature and from going away from the plate, right. And it is, or we can say there's basically thermal energy which is being transferred across the boundary layer. And I think we kind of touched upon the fact that if there is the velocity field, the temperature field is actually connected to the velocity field, which therefore means that if we can solve for the velocity field, we can also solve for the temperature field, right. We kind of did a little bit of math and derivations in the couple of modules earlier, right. So, let us sort of look at that, and I will jot down the points point-wise as to what exactly we're looking at, and then go ahead and do some math. There is some detailed derivations involved, which I will probably not do here, and I will post those online, okay, for your reference, and you should be able to check that, okay. So, let's call this today. So, therefore, so we're basically talking about thermal boundary layers, right. Well, I'm going to head this, and hopefully you will understand what I mean as we go along, okay. So, this is without, okay, coupling of the velocity field right with the temperature field. Right. So, couple of things. So we will basically extend the study of boundary layers in terms of velocity to also include temperature, okay. And how do we do that, okay? So, we will assume, okay, we shall assume that temperatures or say heat, right, heat is transferred okay to the surroundings or which basically means the surrounding flow field, let's put it that way, surrounding flow field, okay, through the walls. Okay. So, basically heat is transferred to the surrounding flow fluid through the wall. So, therefore, as so basically there is a momentum transport, right, across the boundary layer. There is also heat which is being transferred. So like due to the momentum transport, right, we have a velocity boundary layer, right, velocity profile. So similarly we will have a temperature profile. So therefore the velocity profile is the boundary layer as we know it. So this one where heat is transferred, so and we have a temperature difference across the boundary layer, that is basically what we call as the thermal boundary layer. Okay. And at high Reynolds numbers, okay, this will exhibit the same properties as that of the velocity field. Question is why, and think about that. Okay. And what does that exactly mean? Although we'll kind of talk about this a little later on, but let's sort of write this down. If I mean so at high Reynolds number, right, the thermal boundary layer, right, exhibits similar properties, right, as that of the velocity field, right. So, what I kind of, let me just elaborate on that a little bit. So, for example, this is a flat plate that we are looking at, right, and say this is our velocity profile, right. So, this is our velocity profile. Right. So, in this particular case, what we have said so far is that in here, right, nu is not 0, and outside of the boundary layer, you can neglect the coefficient of viscosity, right. Now, again, so now the thermal boundary layer, of course, will have a different, delta of the thermal boundary layer will be different. So, similar to this, okay. So, if I draw a similar picture, okay, the values will probably be different. So, this is a velocity field across the boundary layer, okay. Let us, so it will be like we said similar, but without commenting on it, I am going to just draw it that way. So, this is essentially my and there is going to be a temperature profile. So, we will look at that. We will look at that, there will be a, say, a temperature profile, and this is T. So, we will look at that, okay. We will see how this will look like. Is this a correct profile or no, okay. As of now, let's just say that the lambda, right, which is thermal conductivity, this is not insignificant here, and lambda can be ignored, right, which is away from the thermal boundary layer. Now, the point is that, as you can see, there is a velocity, right, and there is a temperature, right, profile. So, physically there will be a mutual coupling between the two, don't you think? Because you have, the way to look at that is basically you have flow coming in, right? You have flow coming in, this way. You have flow moving this way, right? And you also, and this flow is also has a temperature profile, right? Which, kind of basically saying this is temperature tau wall, right? This is something here and something to infinity somewhere there, right. So, there is a certain, and this kind of a differential temperature being different at different heights can only be possible if there is a certain heat exchange. So, heat is also a fluid, and as it can flow. So, therefore, there is a coupling between the two, right. So, there is a coupling between the velocity and temperature, right? So the heading says that we're going to study this without coupling of the velocity field and the temperature field. I guess that's to just say that we're going to deal with less math, and probably, comparatively easier math when we kind of do it without the coupling. So that's the only objective. Okay. So, so what we'll do first, okay, let's just say, firstly, what we will do, okay, so we will study basically a decoupled flow field, okay, meaning the velocity and temperature are not coupled, okay. So we will study decoupled velocity temperature flow field. Okay. The next thing is okay. Now, physically, of course, you can see that we are kind of making an assumption, right, that velocity and temperature. Now, the question would be, why would, of course, I said, instinctive, like even by intuition, you can think that I have a velocity, and why would, that be affected by the temperature. Now, you see, again, the coefficient of viscosity, the nu here, that itself is a function of temperature and pressure. Right? So, if there is a temperature difference, even that's going to change. And if the value of mu changes, if mu is now with respect to temperature, then automatically your velocity profile is also going to change. Right? So, if we're going to say that study the decoupled velocity flow field, right? If you're going to say that, then this is possible only, right, if we consider that the density rho, viscosity mu, right, are constant, right, and they are not functions of velocity or velocity and temperature. Okay, velocity and temperature. Pressure and temperature, right? Now, this kind of again throws us off guard, because you're saying that these are going to be constant, okay? If these are going to be constant, how is this going to be constant? Because you're saying there is a temperature difference. So, in the sense that there's a variable temperature, right? So, if the temperature is varying, then how can how can kinematic viscosity remain constant? Well, this is we will assume this. So for that, what we will assume is that temperature and pressure variations are small that's something we can assume, right? So basically we're going to say that the temperature and pressure variations are very small within the boundary layer. So therefore, based on that, we can say that the kinematic viscosity is constant, not a function of pressure and temperature, and hence we can study this sort of behavior of the temperature field and the velocity field as a decoupled problem. We don't have to combine the two. Okay. So, of course, we have already started doing this, and we've talked about the you know, the energy equation and all that. So let us sort of just as a starting point overview, let us look at the you know, the equation that we're going to look at, right? So let me name the, okay, so it's like this: rho Cp u del T del x plus V, right, is equal to lambda del 2T del x2 plus del 2T del y2 plus phi, and phi by nu is equal to 2. Right, plus del V del x plus del u del y square, right? Here, phi is the dissipation function, okay? Lambda is thermal conductivity, okay? Ce is coefficient of pressure, right? So this, the equation that I have written here is, so I'm going to call this way, okay? So this equation is essentially 1 and this is 2, okay? So this is essentially the 2D steady state, you know, you can see. So this is essentially 2D. I hope you've noticed it's steady state, right? Energy equation. Okay, so this is how things look like, right? So now if we have to, so you can see, so you can very well see that you know, here how the temperature is basically, you know, connected with the velocity, and how these terms kind of are all existing at the same, you know, same place. Now let us start from a little, you know, little back, and let us go ahead, go sort of understand what's going on here. Now the energy equation, right? So the energy equation, if I were to write like this, okay, so where this is equal to total energy. So the symbol is basically, capital E stands for energy and the small t stands for total, right? So d dt of E is equal to, that should be simple, right? You should be able to understand that, right? So what is the left hand side here? So what is the left hand side? So this term, right, it is rate of change of total energy, okay. This is heat flux, okay, and this is power, right? So, or sort of rate of change of work, so to speak. Okay, so that is essentially my you know, energy equation, and of course, you know, the way I write this, so I could actually write Q dot dt, right? This is equal to heat supplied to the system, right? And this should be work done on the system, isn't it? So this is work done on the system, right? So now we will draw a simple, little cubic fluid element, which you're kind of familiar with. We've been doing this for a while now. Okay, so say I sort of do that. Okay. 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 There you go. Okay. So A, B, C, D, E, F, G, and H. Okay, and the sides, for example, so say height, okay, that is DC, okay, this is dx, and this is dy. Is that right? So this length, okay, the sides, and of course you have flow which is moving past it. You have flow which is moving past it. Right? Is that right? So now the heat flux vector, right? So heat flux vector, okay, is Q, right, which is equal to Qx, Qy, and Qz, right? And or you can basically say this is, and the unit is of course joules per meter square in a second. Okay, so this is what it is. So Qx, Qy, and Qz. So in the x direction. So if I haven't drawn the axis system here, but I hope you can sort of understand that. So axis system is somewhere like this. Right? So this is your y. Is that right? So once you have that, so the fluid, the heat flux, okay, entering the fluid element, okay, through the face ABCD. So we've got A, so we've got this face that we're talking about. So let's see if I can, show that a little bit. So this is the face I'm talking about. Right? So this is the face that I'm talking about. So what I can write here is that heat flux entering the fluid element, right, through ABCD, right, through ABCD is Qx. You understand that? That's what basically we are doing. So we'll have, so what is entering here is essentially Qx, okay, and what is leaving through the face EFGH, right? What is leaving through that? So let's say, basically, I'm talking about this, right? So what is leaving, and heat flux leaving the fluid element through EFGH, right, is Qx plus rate at which it changes along x, right, into the total length traveled in the x direction, which is dx, as you can see. This is the distance which the heat needs to travel, right. So this should be dx, right. So this is in the x direction, right. So you bring the similar analogy to the y direction, z direction, and so on and so forth. So having done that, so if I do that, okay, so therefore net flux heat into the which is, so net heat flux, okay, which is supplied to the fluid element. So all we have to do is this is, so net heat basically, not the element, is essentially yes, so which is supplied to the fluid element, okay. So net heat flux, so what enters is Qx and what exits is this, right. So net heat flux which is supplied is to the fluid element, yeah, is right. So this, right, and so net heat flux supplied to the fluid element, okay. Therefore, what is the total heat which is supplied to the in the x direction, okay. So therefore, if I to do that, so net, this is the heat flux, so net heat supplied x direction is, so del Qx del x is, and I've got to multiply this by the area through which is coming out, which is dy into dz, right. So that is dy dz, so which basically means dx dy dz, that's nothing but the volume. So it is nothing but dqx del x d, this is the volume, okay. Right, and so let's call this as Qx, okay. Now when I say this, when I kind of say this, that heat is being supplied to the system, even there, I mean, we are missing a sign somewhere here, right? When you do the math, of course, right? When you do the math here, so you're basically going to do Qx minus this, Qx minus this whole thing. So you will get a minus sign here, right? Which is fine. But what I would like to ask you here is that explain this conceptually. You know, mathematics wise, yes, you will get a minus sign there, but I would really like you to explain this conceptually. Okay, so think about that. Okay, so therefore, if I therefore write this dV, so this is in the x direction, as you can see, hence total supply. So therefore, I denote this by with a subscript x, as you can see, right. So I denote this, the q dot, right, q dot with a subscript x, and you have qx and you know, del qx del x, okay, and dV is the volume of the element, volume of the fluid element, okay. So therefore, total supply of heat, okay. So total supply of heat is essentially q dot, okay, which is equal to del qx del x plus del qy del y plus del qz del z volume. Okay, this, and as we had written this, this is the heat flux vector, right, and this, what I see, is essentially the divergence of that vector, isn't it? So therefore, I can also write this as, right, I can also write this as q dot is essentially equal to minus, okay, divergence of q, right, into the volume. Okay, is that right? So what we're going to do is keep this, right, for our reference, and this is this. So, so as you can see, we've got some expression for q dot, as you can see here. So we got an expression for q dot, right, in terms of, you know, the, in terms of the total volume and the flux vector, right. So let me stop here, and we will start with the you know, energy, and look at how, what we will do with that. Okay. So right now I will stop here. Thanks.